Okay, so in the last video, we looked at the giant ionic structures. Today we're going to move on to our giant covalent. So just to remind you, covalent is split into two parts. The simple molecular, which are the ones we usually draw in our little diagrams, and the giant covalent, where we have specific types we have to learn about. And then later on, obviously, we'll look at metallic again. And again, our focus is on the physical properties of these chemicals whilst looking into what the structure's like. So in our giant covalent, one of the first substances we have to look at is diamond. So diamond is made purely of carbon. It's only got carbon atoms in. As you can see, it has this structure here where one carbon is joined to 4 other carbon atoms. And it's only got these strong covalent bonds. And it repeats over and over and over again, this giant lattice, again, this repeating unit, but this one is containing atoms because we are looking at a giant covalent structure. And the pattern carries on in every direction to produce 4 of each of them. So if we have a little look on here, this is our diamond structure. As you can see, it repeats again and again and again. If we take one that is towards the middle, you can see it's attached to 1, 2, 3, 4 carbons. And it's very strong. The bonds are very hard to break. Each bond is a covalent bond. And it makes it quite hard. Okay, it's pretty difficult to squash our giant covalent structures. So they are usually very hard substances. Diamonds are one of the hardest substances we have. So they are very, very, very strong. Similar to diamond, we have silica or silicon dioxide, which is actually sand. It's what makes up quartz and lots of rocks we bring down. And you can see the silicon SiO2, the silicon atoms and the oxygen atoms. Each silicon, like the carbon atoms, is attached to 4 oxygens. So the shape is very similar, just a bit more spread out because you've got the oxygens in between. So again, we know this sands, rocks are very hard because they have the strong covalent bonds between atoms again. So because they're all joined by strong bonds, they have high melting points and they are hard and strong. They are very, very, very difficult to melt, to scratch, to break apart. Okay, very high melting points. Now, it's worth noting, because all of the giant structures are atoms, there are no charges. Okay, all of the atoms are uncharged and all of the electrons are caught up in the bonds, so they will not conduct electricity. So there is no way in our diamond structure for electricity to be conducted. It is all the electrons are trapped in the bonds because they're all shared, and the carbons are uncharged, they're atoms, so there is no conducting of electricity in diamond or silicon dioxide. There is, of course, an exception. So graphite is our big exception here. Graphite is also made entirely of carbon. It has a very, very different structure. It has these layered structures you can see here, where each carbon is joined to 3 other carbons with the strong covalent bonds. So these bonds are the same as the diamond ones. But in between each layer is electrons, a weak bond of the single electron left over. So if we remember, carbon has 4 electrons. They would share 1 to each bond, 3, so they'd have a spare one holding the sheets together. So there are strong bonds between the carbons in the layer, but weak bonds between the layers. So because they are weak, the bonds between the layers, we can slide the layers over one another. And this is why when you get a pencil, you can essentially, the pencil will rub off one of the layers, leaving it on the paper, so that you get the trace left behind of the graphite. So the layer structure allows it to be quite soft, unlike other giant covalent structures, because you can flake layers off. Also, because we have these electrons in between the layers, these electrons are not trapped in bonds. So remember, the electrons in our bonds are trapped, so they're not moving anywhere. These ones can move along the layers. They're only bonded to 3 others. There's a cloud of electrons between the layers. and we call them delocalized electrons. And those delocalized electrons allow it to conduct electricity. So if we have a quick look at our graphite, this is what our graphite structure will go. So these are, the red ones are our layers. These are our strong covalent bonds. So these electrons are trapped in the bonds. And you can see it makes a little hexagon, so each carbon is attached to 3 other carbons. The yellow bonds are where our sea of delocalized electrons are, so they are between the layers. So you should be able to see we could slide these layers across one another because these bonds are quite weak. And these 3 sea of electrons in between, obviously they're negatively charged because they're electrons, they are what allow graphite as the only non-metal that conducts electricity. It's not brilliant at conducting electricity, but it's pretty good at conducting electricity. So our main issues with graphite, which remember is an exception, the strong bonds between the atoms, so our covalent bonds, these 3 ones, give it a high melting and boiling point, the same as the diamond. But the weak bonds between the layers making it soft and slippery. We can slide those layers over one another quite happily. And those electrons, that sea of delocalized electrons between the layers, means that it conducts electricity, which is why we can use them for things like electrodes and so on. So, in summary, for our giant molecular structures, they are generally atoms joined into giant molecules. So remember, our ionic had only ions in it. These have only atoms in it. They are hard, strong solids. They don't dissolve because they are giant structures that are made of very strong covalent bonds, things like diamond, and graphite is an exception. So our description of them, all pretty similar, but graphite behaves a little bit differently. And obviously we need to split our giant covalent into 2 bits. Normal giant covalent, which have the high melting and boiling point with the strong bonds between the atoms, and the ones that never conduct electricity because there's no electrons or charges to move around. Remember, the electrons are all trapped in the bonds, and the atoms that it's made for don't have a charge, so there's nothing to conduct the current. And graphite, our exception, which has a high melting and boiling point because it still has a strong bond between the atoms. Those covalent bonds between the 3 carbon atoms to the one in the center are still strong, still gives a high melting point, but it is soft and slippery because we have those layers that are weak, that we can slide the layers apart. And it conducts electricity pretty well because, again, we have that sea of delocalized electrons between the layers that can carry the current for us. Now, there is one other semi-giant covalent structure that exists. It looks like this. We call it a Buckminster fullerene. It was only discovered sort of in the late 80s. It's, again, made entirely of carbon. And you should be able to see that each carbon is attached to 3 other carbons, a lot like the graphite, but it's curving round on itself, so there's no layers here. So it's sort of giant covalent because there's lots, there's 60, carbon 60, there's lots of carbons in this. But obviously it's not like diamond because it's not a infinitely big structure. It's not like graphite because it's got the layers, it's a little bit different. Has similarities to graphite with those 3 bonds. That means there must be electrons moving around inside this. So it does have a cage-like sea of delocalized electrons on it. It's still got the strong covalent bonds between each of the carbons. So it's going to have a high melting and boiling point. But again, it could be quite soft and slippery because if you have lots of C60 together, they roll over one another.